This is page 67 in your packet for chapter 4, and I'm going to go over this homework with you. Hopefully you've already done yours. The first thing that you need to do before you even do this page, and hopefully you've done this, is you need to go back to study the page before this, which is page 66. On that page, what you're going to see is you're going to see various wavelengths, and they're all going to be from the longest to the shortest, and there's additional ones on there. And what you need to realize is that when you have radio waves and microwaves, that those are very, very long. And then at the other end, X-rays, gamma rays, those are very, very short. So here is the approximation of, for instance, a radio wave. It's 10 to the 8th hertz in frequency, and the waves are about 1 times 10 to the 10th nanometers. Over here, though, we have higher frequencies, and we have much, much, much smaller wavelengths. So when you're looking at something like this, what you need to be thinking about is, okay, if I have gamma rays down here, gamma, those are very, very, very short. Okay, so I have a short wave. That means I have a high frequency. And so going back then, C equals lambda nu. Wavelength and frequency are inversely proportional to each other. Now, as far as energy, if we have a high frequency, that means we have a high energy. So energy is directly proportional to frequency. And so we have two different equations that we can use, one to relate wavelength and frequency and the other to relate energy and frequency. So when you're looking at these questions up here, and they are actually pretty simple questions, but you're going to have to answer these on your test without this, because I'm expecting you to at least know these minimum waves. You need to know the visible light spectrum. Just say, okay, Roy G. Biv, red is going to have infrared to the left of it, violet, UV. And then you simply need to know that radio and micro are longer, radio being the longest, X-rays and gamma rays are shorter waves, and gammas are going to be the shortest. So try to imprint that upon your brain, because you do need to know this. Do you need to know exact wavelengths and frequencies? No. So in this first question here, I'm asking you to determine in pairs here, which of these have shorter wavelengths. So what you want to do ideally is you don't want to have this in front of you. You want to be able to do this without looking at this. But I'm going to have this up here to refer to. So infrared and microwaves, which ones are shorter? The shorter wave is going to be toward this gamma. So infrared is going to be the shortest wavelength. Here, radio and X-ray. Well, we all know radio waves are very long, or if you don't know it, you need to know it by now. And then X-rays are very short. So X-rays here, shorter wavelength, gamma or radio. Well, we got gamma. And then UV or microwaves. Well, UV is on the other side of the visible light spectrum on the blue side. And so that's going to be shorter. Micro are down there with radio waves, and they're longer. Now, again, you'll have to do this on your test. It's going to look pretty much just like this. I'm going to change the order and change some of the examples here so that you have to think them through. You just don't memorize this and take it to the next place. You've got to be able to logic this out. So now if you look at this question, number 1 says, you're going to circle shorter wavelengths. So if you're circling shorter wavelengths and you look at the next question, you see the same things. I've put the same things down here. But now I'm asking you, okay, so if you circle the shorter wavelengths here, which one of these different types of radiation are going to have higher frequencies? Well, if your head is in the game, what you're going to do is you're going to say, oh, wavelength and frequency, they have a relationship with each other. And so shorter the wavelength, the higher the frequency. What that means is that you have something that's inversely proportional. So this is going to be shorter wavelengths over here. These guys down here are going to have higher energies. Okay, the longer the wave is, the lower the energies. So guess what? Since these guys are shorter up top, that means they're going to have higher frequencies. Now, if you're having trouble remembering what frequency is, go back and look. But remember, that's how many times a set of waves, a series of waves for a particular radiation is going to travel, or are going to travel past a certain point in a given amount of time. Got it? So the next one, identify the type of radiation in each pair that has a greater energy. Okay, so we have energy here. So we know that at the gamma end, high frequency, we have our higher energies, radio, we've got our lower energies. So shorter wavelength, higher energies. And again, we have a relationship there. Okay. So greater energy is going to be more toward the gamma. So greater energy, we're going to have here green. Okay. Because it's going to be green. Here's yellow. Greater energy. Okay. So this wave here, the wavelength 1 times 10 to the 9th nanometers, that's going to be bigger, a lot bigger than 1 times 10 to the 5th nanometers. This is a smaller number. So since this is a shorter wavelength, that's going to be your greater energy. Violet, okay, violet light on the blue end of the spectrum here is going to have more energy than red, which is over here toward the radio end. So here we're going to have violet light has greater energy. And then down here, you have to do a little bit of converting. So when you convert here, what you have to remember is that 1 megahertz is going to be equal to 1 times 10 to the 6th hertz. Okay, so if you just do a quick conversion there, what you're going to find is that when you have a number like 1000 megahertz, well, you can just set up a dimensional analysis problem. You don't even have to think about it too much because this is magic. Okay. So this is going to be your 1 megahertz. And this is going to be equals to 1 times 10 to the 6th hertz. So think about this. This is really 1 times 10 to the 3rd power. So if you're multiplying this 1000 times this 1 times 10 to the 6th, you add your exponents. This is going to give you 1 times 10 to the 9th hertz. You have to be able to do this. So use dimensional analysis, because sometimes when we're thinking things through, we get a little bit confused. But dimensional analysis, as long as your conversion factors are correct, you have the correct equalities and you have the correct units on top and the bottom, it's hard to get messed up. So here we have 1 times 10 to the 9th, and that's going to be hertz. And we're comparing that larger frequency to the lower frequency. Okay, so what this means then is that this higher frequency wavelength is going to have greater energy. Okay, now you can see here again, I've pulled something that's pretty much about the same thing that I just did up here. Greater energy, higher frequency. All right, so if energy and frequency are proportional to each other, that would mean that your higher frequency, green light, is going to have greater energy. Okay, higher frequency is here. That is greater energy. Violet, and then your 1000 megahertz. So you can see there, I set this up for you, hoping that you could see that you would have some relationships here that you could work through. So hopefully you can do that on the test. Now, for the problems below in number 5, this is something that many of you are really slacking on. You've got to show all your work. It has to be very, very detailed. All variables need to be shown. The basic equation must be listed. And if you have an equation where you have to use a different variable than what is on the left of your basic equation, then you have to write a rearranged equation with the unknown variable to the left. Okay, you need to plug in all the numbers plus the units into the rearranged equation, not the basic equation, and solve it using the correct amount of significant figures, no numbers without units. So do not take shortcuts, because every single time you take a shortcut, I dink you on it. Why? Well, it's not only because I'm mean, it's because I'm really trying to get you guys into a groove on problem solving, so that when you get to physics, you can fly through physics. When you get to college, you can fly through your science courses. If you know how to solve problems correctly and you know how to assign them variables, you will be so much further ahead than the next guy. And we know this because we have students that come back to us and they tell us this all the time. So we have here a yellow spectral line, sodium. You'll see that in lab soon enough. And the sodium wavelength is producing this much energy. And so we want to know what the frequency of that is. Now, Here's what you have to do. As soon as you see this energy, put an E there. It's in joules. You guys know that joules measures the amount of energy in something. Frequency, this is going to be new. Write that down. And then, of course, hertz is going to be that unit. And I might not always tell you what the units are here. So you just have to keep your eyes open. So as soon as you see this E and you see this new, you know that they have a direct proportionality to each other. The higher your energy, the higher your frequency. The equation then that's used is E equals Planck's constant times nu. And so in this case, what we want to know is the frequency. So we have to divide, we have to change the frequency so it's on the left-hand side. We divide both sides by Planck's constant. And there we are. So this is the rearranged equation. So I go through this all on here, but what I want to have you do is kind of think ahead, and then it's going to be easier to feed in the blanks. Write it down. So we have a list here, and so our energy, E, is going to be 3.37 times 10 to the negative 19th joules. Everything's got to be in the same place. What are we finding? Frequency in hertz. What's going to tie that together? Planck's constant. If you don't label what these are, it makes it so much harder for you, and students are constantly trying to use the wrong equation to solve. So Planck's constant going to be given to you. So what's your basic equation? This is what it is. If you have to rearrange, your rearranged equation goes here. I just went through that. And this is not going to hurt you. So we got to plug this in. We're not plugging it into here, though. We're plugging it into the equation with the unknown on the left. So frequency is equal to, come back over here, make sure you double check it, 3.37 times 10 to the negative 19th joules. And we're going to divide that by Planck's constant. This math is not hard. It's just getting your brain to think about problem solving in a very, very definitive manner. So is this a frequency unit? It sure is. This is waves per second, which is the same as this, which is the same as this, which is the same as hertz. So when you get your calculator answer, then I'm not going to go too far out with this, but your calculator answer is going to be 0.5086, blah, 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 more stuff, times 10. Now your calculator is not going to tell you this. You have to think it out. Negative 19, and write it out. It's not going to make it any harder if you write it out. I'll make it easier. So negative 19 minus negative 34. So you know what's going to happen here. So if you're adding 34 onto negative 19, that is going to give you 15. It's going to give you times 10 to the 15th power. Now you can do this on your basic calculator very easily, which is why we've taught you to use scientific notation with the 4-function calculators. Now, this is not your answer. You go back to here and you see energy has 3 significant figures. Therefore, it does not go away ever. You need to keep 3 significant figures here. So if you do, you're going to keep this 5 and this 0, and this 8 is going to change to a 9. That would be 1, 2, 3. However, your decimal has to change places. This value here, this coefficient is less than 1. Your decimal has to go after the first whole number, and then whatever else follows, the rest of your significant figures. Then you just think for a second, okay? I've taken this decimal, and I've increased the value of this number by 1 power of 10. So what does that mean? That means I go from 15 to 14. I just take away 1 power of 10 because I added 1. So this is going to be times 10 to the 14th. And don't leave it at that. Your units are hertz. This does not take a lot of time. You can see I don't have a lot of writing. Everything is very clear. So this is kind of like in English when you're writing a paragraph. Okay, so this is sort of like your topic sentence. And then here you're laying out what you need to keep in mind to address this topic sentence. Here you're at the meat of the paragraph, and you're describing exactly what's happening in relationship to your topic sentence. So you're getting everything organized, you're getting your thoughts down on paper, and you're laying it out for somebody. And then you're going on to complete your paragraph, and this is going to be close to the end of your paragraph. It's almost a summative statement, but here at the end, that's where you're going to end. So you don't just come up with an answer and plop it down there. It's just like writing a paragraph, or essentially telling a story, either way. So the next question is calculate the electromagnetic radiation's wavelength. So I say, okay, wavelength. What is that? And that's lambda. Okay, and it's going to be in meters. So mark your paper up. If the frequency is 7.500, wow, that has 4 sig figs in it, times 10 to the 12th hertz. So frequency, folks, this is going to be new. So as soon as you write those down, you're like, oh, okay, wavelength and frequency. I'm not going to use this equation. This is energy and frequency. I have to use C equals lambda nu. Wavelength and frequency are inversely proportional to each other. So we keep rehearsing the same things again and again with these worksheets. So what are we going to do? We're going to make a list, and you have to scrunch your writing up if you have big writing. Try to keep it neat. So I'm going to put down my, let's say, okay, we got your, given frequency first, sorry. So it's 7.500 times 10 to the 12th hertz. I like to write these out here. I forgot to do it, so I'm just going to add it into the side. And then I want to know the wavelength. So it's question mark wavelength equals meters, okay, however many meters. Now, I have to put that there. It should go over here. You're putting all your information together here. So if something else is involved, in this equation, you also list that. If it's a constant, doesn't matter. You list it anyway. You don't leave it up to somebody's imagination. That's a key part of your story right there. All right. You make sure you know that speed of light. So what's your basic equation? C equals lambda nu. You're never going to be solving for speed of light. So you're going to have to rearrange, and you're going to have to solve for wavelength. You go up here. Yep. Wavelength, meters. Got it. So your unknown variable has to go to the left. I will dock points if you can't get it to the left. Then what you're going to do is you're going to divide both sides by frequency. And there we are. Plug it in. So you go back here. And you can do a double check. Make sure you pulled the right number of sig figs down. You have the right unit. Make sure that you're solving for wavelength. It never hurts to go back. So here's your plug-in. Wavelength equals 3.00 times 10 to the 8th meters per second. And then we have frequency at the bottom, denominator, 7.500 times 10 to the 12th. And this is hertz. So remember, hertz is waves per second. So this guy here, denominator of a denominator, actually goes up here. And when that happens, seconds cancel. You're left with meters. All righty. So you're going to go ahead and get your calculator answer. Now, your calculator answer essentially gives you a number. It's like, whoa, yeah, that's great. So you're actually going to get a 0.4. You're like, ooh, 0.4. I don't have to worry about sig figs too much. But you do, because you have more sig figs over here than this answer shows. You will have to insert placeholders at some point. Let's look at the exponent. We are dividing, so therefore we subtract 8 minus 12, and that's going to give you -4. So this is times 10 to the -4th. Now, we know that we're just going to count sig figs here, 3 and 4, even though technically we should probably not do that, but we're just going to go for the easiest number to control this with. So 3 sig figs and 4 sig figs you're dividing. You're going to stay with 3 sig figs, okay? So over here then, what you see is that this is 0.4. Well, that is not going to work for you. So you have to have a whole number with something else following it in scientific notation in order for it to be in correct notation. So that decimal then would slide over here However, you have to put 2 zeros after the decimal so that you can show 3 significant figures. Here you only have 1 sig fig, but here you've got 3, and here you've got 4, so you go with the fewest amount. So I can't just change this coefficient and not address the exponent, so I will do that right now. So here is your coefficient. You made the coefficient larger by a power of 10. So in other words, you multiplied by 10. If that's the case, the exponent has to get smaller by a power of 10, or you have to essentially divide by a power of 10. Now watch it, because when this -4 gets smaller, it gets further away from 0. So it's actually going to be -5. So everything's great up until now, and you just have to go back and you have to say, okay, are my units meters? Okay, is wavelength measured in meters? Yes, it is. And do I have that right? Now, if you're doing this on a test, I would strongly advise making sure you go back and you check your significant figures. Many students are just disregarding them completely, and it's really affecting your grade right now. So make sure that everything you do, you put a unit after every number that is measured, and you always use the correct amount of significant figures. Alrighty, so that's page 67.